Howdy, Pre-Cal. It is Miss Kosh, and today we are graphing, well, all 6 trig parent functions. We've kind of already done a sine and cosine with spaghetti, so, and now we're going to jump in. We're going to use those 2 to help us generate the other 4. Okay, so what we discovered with spaghetti was that the sine curve starts to make this sort of shape. And so I want you to focus on 5 points, and those are, we have this little abbreviation, the mid, the high, the mid, the low, the mid. Okay, so the 5 points I want you to consider are the one here at 0. This is 0, 0. I want the one here at pi over 2, 1. So notice this graph is labeled with tick marks. You know, they labeled the tick marks. You could also label, and actually you don't have to label that 0, but that is there at the origin, 0, 0. You could label it with the tick marks like they are here, or you could label it as pi over 2, comma 1. That sort of thing would be fine. So that was we have our mid, our middle, our high, our middle, our low, and our middle. And those 5 points, they just start repeating over and over and over again. And what you'll notice is that when you think unit circle, you've got the first one, the middle, starts here, and then it's the high, and then it's the middle, and then it's the low, and then it's the middle again. Okay? And so it takes us those 5 points around the unit circle. Our period is how long it takes it to do everything it's going to do. Let's write that down. How long it takes to do everything it is going to do. That is the period. And so if you look at this, our curve, we did the middle, the high, the mid, the low, the middle, and then after that, it's just repeating the same process over and over again. So how long did that take? It started at 0. It finished that process over here at 2 pi. This is the point 2 pi, comma 0. And so the period of sine is 2 pi. The amplitude is how high above, and actually, or it could be below the midline. Do we go? So the midline here is our, is our middle. Right here was at 0. Well, we went 1 unit up. We went 1 unit down. Okay. So the amplitude is 1. Do you see any asymptotes? No. You will always tell me none, or you could write NA. Okay, and so this is what we look at here with our parent function of sine. When we talk about the zeros, you'll notice I have a 0 at 0, I have a 0 at pi, I have a 0 at 2 pi, I have a 0 at 3 pi. The next one would be 4 pi. We have a 0 at negative pi. We have a 0 at negative 2 pi. And so our zeros here happen when every pi units apart. And so what we can say here is we can say x is equal to pi k, where k has to be an integer. And so this notation means k is an element, that's not an element of the integers. Mathematicians are inherently lazy, efficient people. We will use 3 little symbols right here instead of writing out that whole sentence. And so our zeros happen, so notice if I plug in the integer 0, 0 times pi is 0, we have a 0 at 0. If I plug in 1, I am at 1 pi. If I plug in 2, I'm at 2 pi. If I plug in 3, I'm at 3 pi, etc. Okay, so so that is where we find the zeros. Coming back to the domain, there are no restrictions on the domain of sine, so the domain is all real. Negative infinity to positive infinity. The range, well, we went as low as negative 1. We include negative 1, so we're going to have that hard bracket, and we go as high as positive 1. And there we go. Cosine behaves in a similar way, or it has a similar shape to sine. You'll notice they're both kind of these wavy things. But on this one, our 5 points are going to be the high, the middle, the low, the middle, the high. And once again, how long did it take us to do that? It took us 2 pi to do that. How high did we go above our midline? 1. Do we have any asymptotes? No. You could write none or you could write NA. So I'm writing both. And you'll notice, once again, these 5 points correspond to the 1, 2, 3, 4, 5 places around our unit circle. Okay, so now where are our zeros? Well, this time we have a 0 here at 1 pi over 2. And then we have a 0 here. I don't know if you can see the label, but it's now at 3 pi over 2. This next one here is at 5 pi over 2. The next one here is at 7 pi over 2. And so you'll notice how far apart are they? Well, what I've done is I've added, when I start at 1 pi over 2, I add 2 pi over 2, I get to 3 pi over 2. From 3 pi over 2, I add 2 pi over 2, I get to 5 pi over 2. From pi over 2, so what I'm doing is I'm adding each of these are pi units apart. And so what we will say for this one, the zeros of cosine, are at pi over 2, plus they happen every pi unit, so we say plus pi k, where k is an element of the integers. Okay, they're pi units apart, but they don't start at 0 like the first one did. They start at pi over 2. Okay, the next little bit, our domain is negative infinity to positive infinity, and our range, just like sine, is -1 to +1. Okay, so now we're going to use everything we have here to then generate the other 4 trig functions. Okay, so we remember the reciprocal identities are these two. Cosecant is the reciprocal of sine, it's sine's buddy, and secant is the reciprocal of cosine. And tangent, we know it to be sine over cosine, and cotangent is the reciprocal of that, so cotangent is going to be cosine over sine. So these are going to be really helpful as we keep going. Write cosecant in terms of sine and cosine. Well, we just said cosecant is 1 over sine of x. So where is cosecant undefined? Keep in mind, you're not Chuck Norris. You can't divide by 0. So cosecant is undefined anywhere sine of x equals 0. Well, where does sine of x equal 0? If only we just wrote that down, which we did. Sine of x here equals 0 at pi k. Okay, so it's going to equal 0 when x equals pi k. Where is cosecant 0? Well, in order for a number to equal 0, you have to have, like, if you have a fraction, the numerator has to equal 0. Can 1 ever equal 0? Well, if it can, I'm going to give you $0 million, and you can give me $1 million in return, because they're never actually equal. If you think they're equal, I will take $1 million from you. Okay, so where is cosecant 0? Nowhere. So it's never going to equal 0. And so this is how we will divide. So cosecant is the reciprocal of sine. So sometimes we start, I'm going to graph sine in pink. Okay, so sine looks something like this. Remember we had our middle, our high, our middle, our low, our middle. There was one period. Okay, so that reminds us what shape we should follow. Well, so what we have is if at these points here, at our zeros, I'm going to try and, if I plug in something where I get a 0, I end up with 1 divided by 0. Can we do that? No, we're not Chuck Norris. So what's going to happen in my graph? What's going to happen in my graph is that I get an asymptote anywhere sine had a 0. Okay, so all of these zeros in sine are going to give me asymptotes for cosecant. Okay, so now the next thing, we have a point right here that has on sine, it's got a y value of 1. So what is 1 divided by 1? Well, hopefully you know that 1 divided by 1 is 1. Well, what happens if I'm looking at this point down here and the value is -1? What's 1 divided by -1? Well, it's also -1. So what's going to happen is all of these highs and lows of sine become actual points in cosecant. Okay, so now the next thing, what's happening here is these values, how do I want to show you? Does this work? No. Okay, these values here are starting to get smaller and smaller and smaller as they get closer and closer and closer to 0. Well, if I have 1 divided by something really, really small, like if I have 1 divided by, no, I don't want to do that. If I have 1 divided by something really, really small, the reciprocal of something really, really, really small ends up getting to be really, really big. And so this is going to start, these are all going to flip like this and live between these asymptotes. And if I have something 1 divided by something really negative and small, it's going to end up getting really negative and big. And so these go this way. Okay, and so each one of these, once you know what your sine curve looks like, your cosecant curve, the cosecant is only in blue. So what I have in blue is what the cosecant graph looks like. My kids years ago started calling these Lego hands. So I don't know if you can see that they kind of look like the hands of a Lego character. And so Here we go. These are, we can, these kind of, this one up here, these look like waves. These look like Lego hands. Okay, and so the period, how long did it take it? Oh, you know what? I didn't label things. I should. On this one, we're going to label, here was 0, this was 1 pi, this was 2 pi, and so, and here comes 3 pi. I don't necessarily have to label that, but what happens is my period is going to be, well, how long does it take it to do everything it's going to do? It does an upward Lego hand, and then it does a bottom Lego hand, and then after that it just keeps repeating. So the period of this are these two little Lego hands, one going up and one going down. And so how long did it take it to do that? It went from 0 to 2 pi. This has a period of 2 pi. And now we are about to discover the only functions, the only trig functions that have amplitude are sine and cosine. So you're going to tell me none when I ask for amplitude on cosecant. The asymptotes, well, where did they happen? They happened where we were undefined, over here, okay? So the asymptotes are when x is equal to pi k. And technically, we should write down this kes every time. I'm going to say write it once on your paper and we'll be good. The domain, well, notice the domain is going to be everything except the asymptotes. So we will say it's the set x, such that, and we do a little colon, x is not equal to, what were my asymptotes? Pi k. And that's how we write the domain. Notice there are infinitely many intervals here, and we ain't wow, ain't nobody got time to write all those down. Okay, that's what I was trying to say. Now, what is the range? Well, you'll notice the range starts at negative infinity. It goes as low as it's ever going to go, and then it comes up as high as -1. We include -1, and then we have to mind the gap. So we're going to pick this up again. We have a gap. I love that expression. It reminds me of the subways in London, and I actually got to go. I've been saying mind the gap for years, but I actually got to go like a year and a half ago, almost 2 years ago. And they say mind the gap between the train and the platform. So we're going to mind the gap because we have a gap between -1, and then our graph picks up again at 1 and goes to infinity. All right, once we know cosecant, secant is going to behave in a very similar way. But secant is 1 over cosine of x. And so where is secant undefined? Well, it's undefined anywhere cosine of x equals 0. Let's go back to our table. Cosine of x equals 0 at pi over 2 plus pi k. X equals pi over 2 plus pi k. Where is secant 0? Nowhere. That looks, because 1 cannot equal 0. It's never going to equal 0. So you notice in that previous one, we had this big gap here. We never touched the x-axis. Okay, so when we start to sketch this one, we're going to start by graphing cosine. And remember, cosine goes high, middle, low, high, middle, low, middle. Okay, something like, pretend I can draw. Okay, now anywhere cosecant has zeros, we now have an asymptote. This first one was at 1 pi over 2. The next one here is at 3 pi over 2. The next one is at 5 pi over 2. The next one is at 7 pi over 2. I'm tired of going in a positive direction. Let's make things negative. I'm just kind of kidding. Okay, negative 3 pi over 2. Well, anyway, I did make them negative, but I wasn't trying to be. All right, it was funny in my head, didn't play out. Okay, so here are our asymptotes, and now once again, we're going to, anywhere we had a maximum in cosine, we now have a spot where we can branch off to find secant. And so secant is going to look very much like cosecant. It's got all these little Lego hands, living happily ever after, but they're shifted a little bit from cosecant. So how long did it take it to do everything it's going to do? Well, you could think of it as going one up hand and one down hand. If we look at that, we are going from negative pi over 2 to 3 pi over 2. And so that's a total distance of 2 pi. Another way to think about it is that we're starting at 0. We have half of an upward Lego hand. We have all of a downward Lego hand. And we need the other half of the upward Lego hand. And that happened by 2 pi. Okay, so the period is 2 pi. The amplitude is none, or you can write NA. The asymptotes, well, the asymptotes right here are where secant was undefined. That's going to cause clutter. Okay, there it goes. And so the asymptotes are when x is equal to pi over 2 plus pi k, where k is an element of the integers. I'm writing it sometimes, not every time, whatever. The domain is going to be everything else. So it's going to be the set x such that x is not equal to pi over 2 plus pi k. What's my range? Well, it behaves just like cosecant. So it's negative infinity to negative 1. We have to mind the gap and then go from 1 to infinity. Super? Okay, so we've got 2 that look like waves. We've got 2 that look like Lego hands, and we have 2 more. And let's get started. Okay, so this one, tangent is equal to sine of x over cosine of x. Okay, and so where is tangent undefined? It's undefined when you're not Chuck Norris, you can't divide by 0. So it's undefined when cosine is equal to 0, which is pi over 2 plus pi k. We can remember by looking way back here, cosine right here, the second one, equals 0 at pi over 2 plus pi k. Coming back, there we go. Where is tangent 0? Well, tangent will be 0 when sine of x equals 0. Well, sine of x equals 0 at pi k. There it was, pi k. Okay, so we have, what we're going to do is we're going to start to draw this, and we're going to label things. We're going to have a 0 at 0, because if k right here were 0, that would be 0. 0 times pi is still 0. So we have a 0 there, and then when I look at this one over here, I plug in 0 for that one, I have an asymptote at pi over 2. Here's an asymptote at pi over 2. And then I plug in 1 to this one, and I get 1 pi, so here's that at 1 pi. Then I plug in, oh, that's not what I wanted to do. I wanted to delete this. Now I'm going to come over here, plug in 1 here, pi over 2 plus pi is going to give me an asymptote at 3 pi over 2. And then I can come back to the other one. Notice I'm going back and forth. If I plug in 2 to this one here, I now get 2 pi, and that's another 0. Okay, we can keep going. We would have an asymptote at 5 pi over 2. We could have an asymptote at negative pi over 2, and we'd have a 0 at negative pi. And we can keep going until we run out of space or time or desire. Okay, so then what I want us to do is look at this unit circle. Up here in our unit circle, tangent will be positive in quadrants 1 and 3, and tangent will be negative in quadrants, well, this is 2, and this is 4. I just wrote them backwards, whatever. Okay, this is quadrant 1, this is quadrant 3. Okay, so keep in mind this is going from 0 to pi over 2, and then here's from pi to 3 pi over 2. Okay, so you know what? I'm going to do this now while I'm thinking about it. I'm going to change this color. If I try to remember to do it, there we go. So it looks different than everything else. From 0 to pi over 2, all of our tangent values are positive. And so what happens is from 0 to pi over 2, our tangent values are positive, and they start shooting off to positive infinity. Okay, in quadrant 2, all of our tangent values are negative, and so they kind of come from negative infinity, and they're doing something like this as we go from pi over 2 to pi. Then, as I travel here into quadrant 3, I'm going from pi to 3 pi over 2, and they're getting bigger and bigger and bigger, and they go off to infinity as that slope goes off to undefined. Okay, and then these will be negative, and these will be positive, and these would be negative, and so we have negative and positive over here also. Okay, and so this is what the graph of tangent looks like. And we can think, well, how long did it take it to do everything it's going to do? Notice it's a repeating pattern between every set of asymptotes. And so from negative pi over 2 to pi over 2, we have one whole period. That's pi, or you could think of it as going from 0 to pi. Oop, that's weird. 0 to pi, when I look at that, I have the upward part and the downward part, connecting those two zeros. I pretend to stay between two asymptotes, and so our period for this one is pi. You'll notice all of the others had a period, where are these? A period of 2 pi. So tangent is the first one we've seen that it has a period that's not 2 pi. Amplitude, nope, there is none. Asymptotes, well, they happened where we were undefined, so pi over 2 plus pi k. My domain is everything except the asymptotes, x such that x is not equal to pi over 2 plus pi k. I should have written k somewhere, but I already have it. My range, notice, I'm shooting off to positive infinity and negative infinity, so it's negative infinity to positive infinity. All right, we are almost done. We have done 5 of the 6 tangent functions, or not tangent, trig functions, and we're left with cosine. So cosine is, I lied, we're left with cotangent. Cotangent is going to behave similarly to tangent, but not quite the same. So it's cosine over sine, so where is it defined? It's where is it? Undefined? It's undefined whenever the denominator equals 0, because you're not Chuck Norris. You can't divide by 0. And so that's when sine of x equals 0. Well, when does sine of x equal 0? At pi k. When is cotangent 0? That's when the numerator is equal to 0. Well, when is cosine equal to 0? At pi over 2 plus pi k. If you forgot those, you could go back to that very first chart and see that I was right. Okay, so when we graph this, just like we did with tangent, we're gonna plug in 0 and then 1 and then 2 into both of these equations. So when I plug in 0, I get an asymptote at 0. And then I plug in 0 to this one, and I get that I have a 0 at pi over 2. And then I plug in 1 right here, and I get that I have an asymptote at 1 pi. And then I plug in 1 right here, and I have pi over 2 plus pi is equal to 3 pi over 2. And then I have an asymptote when I plug in 2 right here, and this is at 2 pi. And then I'd have a 0 here at negative pi over 2. I'd have an asymptote at negative pi. And this one's 0. You can label 0 or not. It's kind of obvious. And that's the starting bit of cotangent. So now when we think back to the unit circle, we had that tangent was positive, negative when we went through the quadrants. Well, cotangent is just the reciprocal of tangent. So if tangent of theta is equal to, that's not what I wanted to do. Let me say it this way. Let's try again. If cotangent of theta is equal to 1 over tangent of theta, if tangent's positive, well then 1 over something positive is still going to be positive. If tangent were negative, 1 over something negative is still going to be negative. So with this one over here, cotangent, let's do it in green to match the other. Cotangent will be negative. No, it won't. It'll be positive. It'll be negative. It'll be positive. It'll be negative, just like tangent is. Okay, and so this was from 0, pi over 2, pi, 3 pi over 2, we're back to 2 pi, et cetera, et cetera, et cetera. Okay, so and from 0 to pi over 2, we need positive values. So 0, oh, I did this in red and that one in blue, whatever. 0 to pi over 2. So notice that's in this little mess right in that interval right there. So we have to be positive, so we're going to be coming down instead of going up. So from pi over 2 to pi in quadrant 2, we're now going to be negative. So we're doing something like this. So these, and then it keeps repeating forever. Okay, so they look very similar to tangent and cotangent, but they're not facing the same direction. Okay, so be careful with that one. The period, how long did it take it to do everything it's going to do? Well, it did everything it needed to do from 0 to pi. So what did I just undo? I didn't want to undo that. Redo. There we go. So the period is 1 pi. There is no amplitude. Only sine and cosine have amplitude. The asymptotes show up when x is equal to pi k. So the domain is not that, x such that x is not equal to pi k. And the range, it's everything, negative infinity to positive infinity. And now we have talked about the 6 parent functions, 6 trig parent functions. Like, subscribe, comment, and go practice. Good luck to you.